Okay, taking a look at circles and intersecting lines, we're going to look at how to use intersecting lines with circles to solve different kinds of problems that have to do with mostly measures and degrees. And so remember that a circle is a set of points in a plane that are equidistant from a point called the center of the circle. Okay, so all of these points around the circle are the same distance to that center point. Right, we talked about before spring break when we did equations of lines, we also talked about equations of circles. So you might go back and reference those notes a little bit. What that equation would look like. A radius is a segment whose endpoints consist of a center and a point on the circle. So a radius has two endpoints. The center is always constant. The point on the circle can be any of those points. So you would name it like you would name a segment. You have the line up above, CF, CG, CD, depending on, so like if this is your center, this is F, maybe this is G, maybe this is D, so we could even draw another segment, another radius there. A chord is a segment whose endpoints are on the circle. So they go all the way from one side to the other, and they can pass through the center, but they don't have to, as long as you have one endpoint on this side and one point on this side. So if I drew a line from G to F, that would be a chord. You name it again, just like you would any segment, GF, AB, whatever those endpoints are. The diameter is a chord that goes through the center. So if you have a segment that goes from one side to the other and passes through the center, that is a diameter. So in this diagram, it would be GF, and I'm going back up here. Radius is CF, CG, CD. Those are all radius. And GF, this whole thing, is a diameter. AB is a chord. GF, even though it is the diameter, is also a chord. DE is a different type of line instead of segments. So all three of these are line segments. But you can see in this diagram we have two lines that have the arrows on them. A secant is a line that intersects a circle at 2 points. And so it crosses all the way through the circle. And we name it like a line. So you can see up here, we named this chord AB. The secant, though, is AB with the arrows. So going back to chapter 1, unit 1, it's all about the notation. So if you see those arrows, then it's a secant or a tangent. And a tangent is a line that intersects the circle at exactly 1 point. So this right here is your point of tangency. So it's not passing through the circle, it's just touching at point D. But again, it's a line, so we have the arrows above the name. Your point of tangency is where the circle and the tangent line intersect. So point D is where those two intersect. Okay, so looking at the circle, you would need to be able to name each of these items in this diagram. So multiple answers for several of them. A radius, you could say CB or BC. Remember, the order doesn't matter there. Or you could say AC or CA. So either of those answers are fine. A chord also has multiple answers, but remember, notation matters here. So AB is a chord, and AG could be a chord. A diameter on this diagram, there's only one answer, it's AB. But that's not to say you can't draw more than one diameter. This diagram just doesn't have them drawn. So sometimes there's multiple answers there. Remember, a secant goes all the way through your circle. So you have two lines here, but the one that passes through and intersects twice at both A and G is a secant. And then a tangent will only hit once. You could say BE, you can say DE, you can say DB, any 2 points. The order of these can all switch. Your point of tangency, though, is point B. That is always the same in that diagram. All right, so you can have circles intersecting with a different number of points. That will sometimes affect how many tangent lines they have, but don't mix up points of intersection with a point of tangency. So these are intersecting, but they're not tangent at those points. When you have one point of intersection, that's when they're tangent circles. So these two circles only touch here, these two only touch here. Okay, so same with tangent line, it can only intersect once. If you can have 0 points of intersection where you have two circles completely separate, or you can have concentric circles where you have a circle inside of a circle inside of a circle, and they all share a center. So a donut or a tire, or a record, if you guys hopefully know what a record is, but a record is concentric circles, and that's how the needle runs, all sharing that common center. A common tangent is a tangent that two circles share, so it's tangent to both circles, meaning that it hits it at 1 point exactly. So each of these have a single common tangent. These would actually probably draw another one maybe. I'd have to use a ruler and see. So you can look at circles and tell how many tangents they have in common. How many could you draw? So like, for example, this one only has 1 point of tangency between these circles, and so this one only has one common tangent. These two circles intersect, so they don't have any common tangents, but you can draw a line here that intersects that side, and here that intersects these sides. So this one has 1 where this one has 2. Okay, angles inside a circle. So inscribed angles is an angle whose vertex is on the circle and whose sides contain chords of the circle. The arc lies on the interior of the intersection in a circle, and we call that an intercepted arc. There's a really cool relationship between the inscribed angle and the intercepted arc. And so here's what that looks like. Here's your angle. The vertex is on the circle. The chords are the sides of the angle, and then it creates this intercepted arc right here that is flanked on both sides by that by those points of intersection. Now, circles are measured in degrees. There's 360 degrees around the circle. And angles are measured in degrees because they're portions of a circle. So the measure of the inscribed angle is 1/2 the measure of its intercepted arc. So this is half of this, which I think is kind of cool. So for example, if this angle was 34 degrees, then this arc would be 68 degrees. Or if you know the arc is 68 degrees, then you can then figure out the angle is 34 degrees. So that relationship works back and forth. So this is how we notate it. The measure of ADB is 1/2 the measure of arc AB. And so we name an arc just like that. Okay, so this circle has arcs AD. It has an arc at DB. And these are what we call minor arcs. They're less than 180 degrees. Major arcs you would need to name with 3 letters. So if you want to go from A to B but go the other way, then you would say ADB. So that's what's called a major arc. Otherwise, you always go the shortest path. In a circle, a radius is perpendicular to a tangent line at its point of tangency. So remember, perpendicular is going to create that 90-degree angle. And that's what this looks like. So we have your tangent line, M, point of tangency is P. If we go P and draw a line to the center, it will always be 90 degrees. And that is helpful in solving a numerous amount of problems because we then have right triangles. And so B is a point of tangency. That means that this is a right angle, and now we have a right triangle. And we know that this distance and this distance are the same because they're both radiuses. And we can set this problem up and find what the length of that radius is. And so we have this side here, which is 50 plus r, and we have 80 and we have r. So we have A, B, and C in our right triangle. And we recall that a squared plus b squared is equal to c squared. And so we just plug in. So 80 squared plus r squared equals 50 plus r squared. Do not distribute this. This needs to be FOILed. And so we take 50 plus r times 50 plus r. And we distribute that through. So 50 times 50 plus 50 times r plus r times 50 plus r times r. Didn't leave myself enough room there. So sorry that's so sloppy. Hopefully you're listening. And then over here we have 80 squared, so 6,400 plus r squared. Well, we have an r squared on both sides of our equation. So anytime that happens, you can just cancel things out. We have like terms here that need combined. And then we have this here that can be subtracted over here. So 6,400 minus 2,500. And we end up with 3,900 equals 100r. So we can divide by 100. And r equals 39. And that's your radius of circle C is 39. You could always plug that back in and double check to see if 80 squared plus 39 squared is equal to 89 squared, because you have to add those together. It would be a super quick check to do. All right. I wanted to put that out of the way. Tangent segments are common to an external point, means that they're congruent. So if you have a tangent segment from point T to S, and then you have R, and you also draw that to S. So if they go through a common point and they're both tangent to the circle, then these lengths are the same. So RS is congruent to TS. All right, once again, that helps you solve problems because if we're trying to find this x value here, we can just then set this and this equal. So RS is tangent to circle T at S and RT is tangent to circle T at T. Because they have that common point R, we can say that 28 is equal to 3x plus 4. Um, and then we can just solve that out. So 24 is 3x divided by 3, and x equals 8. This section I accidentally somehow doubled it, and I've never fixed the notes, so just ignore that section. All right, but this goes back to that rule that the measure of the angle is half the measure of the arc. So if HF is 90, then HGF is 45 degrees. If this angle is 38 degrees, then we're going to double that. So 76 degrees will be this arc. And then careful on these. So this is 72. Right, so ZW is double that because that's its intersected arc. So ZW would be 144. All right. This angle here is what we're trying to find, ZXW. Well, that intersected arc happens to be the same. And so it's half of 144, so it is also 72. And that will always be true. If two angles share an intercepted arc, then the angle measures are the same. Oops, let's spell that right. They share an arc. All right, inscribed angle is, or an inscribed polygon is a polygon whose vertices or corners all lie on the circle, so they all touch the circle. A circumscribed circle is a circle that contains all the vertices of the polygon. And so this is a inscribed triangle. This is a circumscribed circle. And so the shape inside is called inscribed. This is called circumscribed. Circumference is the distance around a circle. So you're going all the way around the circle and hitting every single point. A quadrilateral can be inscribed in a circle if and only if opposite angles are supplementary. And so we're talking about the quadrilaterals, not the triangles. Those are different. But like this angle and this angle here would need to add to 180 in order for them to both be on this circle. And again, that has to do with the fact that there's 360 degrees in a circle. And so there's 360 degrees total in this quadrilateral. So we're going to split that between opposite sides. So these are 180 and these are 180. All right, so again, we have supplementary angles. Angle D plus angle F is 180. Angle E plus angle G is 180. Notice those are opposite angles. G and F, for example, would be consecutive angles. And so we can use that fact to solve problems. If you don't have two variables, you can just add all four of them to equal 360. But since there's two variables here, we know that x is equal to 80. Back up, sorry. X plus 80 is equal to 180. So x equals 100. And we know that y plus 75 is equal to 180. So y equals 105. Same thing here. Opposite angles, so here and here. So 4b plus 2b is 180. So 6b equals 180, and b equals 30. And 2a plus 2a equals 180. So 4a equals 180. And a equals 45. And that's that for those. So opposite angles are supplementary. Add them together to equal 180. Other angle relationships, you can sometimes have a vertex on the circle of an angle. So here's this angle here. It creates two angles if it's a tangent line. The measure of angle 1 is half the measure of arc AB. So this is AB, and this is half of that. The measure of angle 2 is half the measure of this arc, and that kind of goes with your inscribed angles. It's still half of the intersected arc. If the vertex is inside the circle, not on the circle, but inside of it, it creates some different angle pairs here. So the measure of angle 1, this angle here, is half the measure of DC plus AB. So these two angles here, or arcs here, excuse me, need to be added together and then take half of it. The measure of angle 2, same thing, it's intercepted arc and then the one behind that. So these two angles, remember, are vertical. So it's like taking this one and taking half of that, that would be the measure of angle 2. And then the last one, if the vertex is outside of the circle, then we're going to take half of the measure of the arc's difference. And so we take the big arc, BC, minus this little arc, AC, and it will divide it by 2, and it will give us this angle. Okay, so just some other angle relationships in your circles that you may find useful. So for example, the measure of angle 1 here, again, is 1/2 the measure of this. And so the measure of angle 1 is equal to 210 divided by 2 is 105. Outside of the circle, we subtract and then divide by 2. So the value of x is 178 minus 76 times 1/2. So 178 minus 76 is just 102. And we multiply that by half or divide by 2, and we get 51. So x is 51 degrees. All right, and then last is using some of those angle relationships to find maybe the measure of an arc instead. So remember this. If this angle is 102, this is 95. This angle here would be 102. This angle in this picture, I should zoom in here. This angle right here, think about your linear pairs, would be 78. And this angle would be 78. And we go back to this rule right here. If we add these arcs together and divide by 2, we get this angle. Both angles, it doesn't matter which one. And so 95 plus y times 1/2 is equal to 78. And so we can multiply both sides by 2, and that gets rid of our 1/2. So we have 95 plus y is equal to 156. And then we subtract 95 from both sides. So y equals 61. All right. All right, BZ is tangent to angle C. The diameter, AC is a diameter. The measure of BC is 90. So label, anytime you're getting a list of all this stuff, you can label. So BC, this angle here, is 90. That is going to be the same as your central angle, which I'm not sure I gave you that rule in the, like that's written down. So a central angle is equal to the arc measure. And so if that's 90, then that is 90. So right away we know the measure of angle 1 is 90 degrees. Measure of arc CD, so here to here is 30. D to E is 20. And that's all we know for now. So find the measures. And we know that this is a diameter, which means that this is 180. So if that is 90, then that is 90. Not that that's labeled, but sometimes it helps just to work those out. Okay, so then you just work through using your rules. So remember, like, inscribed angles are half their intercepted arc. So for example, since we know that A to B is 90, we can use the fact that if we have, I thought we had an angle that was inscribed there. We don't. All right, so that's 90, that's 90, that's 50. So now we can find A to E because we have 180, 30, and 20 is 50. So we're just going to take 180 minus 50 and get 130, and that's what A to E is. And now we have all of those. So this angle 2 is inscribed. The point of intersections, or the intercepted arc, is 180 degrees because it's 90 and 90. So angle 2 is half of that. So angle 2 is also 90 degrees. Angle 3 is right here. So its intercepted arc is C to E, which is 50, because it's 30 and 20. So it's half of 50. So it's 25 degrees. Okay, so 1/2 of 50. Angle 4 is right over here. Let me erase some of my markings here. So angle 4 goes from here to here. That's half of 130. So that's 65. Angle 5 is going to be a little bit different because its vertex is inside of the circle instead of on it. So angle 5 is right here. And so remember, if it's inside, you take this one plus this one and divide it by 2. So for angle 5, that's going to equal 90 plus 20 divided by 2, or put the 1/2 out in front of it. So we have 110 divided by 2 is 55 degrees. Measure of angle 6, we could do the same thing with our arcs, but it's also supplementary with angle 5 because those are a linear pair. And so we can just do 180 minus 55. Because they're a linear pair, and we get 125. Angle 7, and you don't always have to go in order here, just going in order. Angle 7 is outside of your circle, so again, you can always go back and look at your rules. If an angle's outside, we're subtracting those arcs, and then we're taking half of that. And so angle 7, we have our 20, and we have a 90. So we're going to take the measure of angle 7 is equal to 1/2 90 minus 20. So half of 70 is 35 degrees. Measure of angle 8. Angle 8 is right here. So again, it's inside of the circle. And we're using 90 and 30. So 90 plus 30. This is angle 8. So 90 plus 30 is 120, and half of that is 60. And then if it has your 3 letters, you're going angle. So FBO, this angle right here, is half of the intersected arc. But it's also, I think that's a tangent line. Yeah, BZ is tangent. So this is tangent. B is your point of tangent C. So this is automatically 90 degrees. We don't need to do all of that. So 90 degrees. And DBZ, where's the DBZ, this one right here. That one is in the circle. And so it's half of the intersected arc. Your arc goes 90 and then 30. So 90 plus 30 is 120. And half of that is 60. Okay. And so I know that's a lot of work, but it's using and applying those rules to work your way around the circle. I apologize for the long video. Hopefully you listened and got something out of it. Have a good day.